So this is conservation of momentum. Wherever you go, there you are. You can't. So we'll see why that's relevant in just a minute. So when we talk about conservation in like environmental science or in biology, we're talking about like keeping things the same or not using things up too fast. In physical science, conservation has a slightly different definition. It still has, I mean, there's obviously some similarities, but we're talking specifically about keeping the conditions before and after some event the same. All right, and when we talk about conservation of momentum, we're talking about the fact that the momentum before has to be equal to the momentum after. Right? The momentum can be transferred from one object to another or multiple other objects, but no momentum is lost. It all can be accounted for. All right? When the two football players hit each other, the final momentum is equal to the initial momentum. So it's 600 on one side, 400 on the other, and then the combination is 200 Newton seconds. None of that is lost. But if you actually measured that momentum, you might find that turns out there's only 100 Newton seconds afterwards. Now, where would that momentum be going if you started off with 600 from player one and 400 from player two, and you expected 200 Newton seconds in the end, but you only got, when you measured it, you only ended up with 100 Newton seconds. Where is somewhere else where that momentum might be going? Hint, look at the third bullet. Nobody? When I say lecture, do people just tune out? Sometimes. So we have these two football players. Player one imparts 600 Newton seconds of momentum. Player two imparts 400 Newton seconds of momentum, colliding at each other in opposite directions. The final momentum we expect to be 200 Newton seconds. But then it turns out we actually measure it. We actually go out there on the field and we measure what their final mass is and what their final velocity is. And it turns out we get a final momentum of only 100 Newton seconds. Where could that other 100 Newton seconds have gone to?
Friction or another outside force.
Yeah. Friction with the ground, friction with each other. The outside force of the compression of the pads. The outside force of the compression of the elasticity of the human body, absorbing it in their rib cage, absorbing it in their brain. This is why football players are so concerned about concussions. All right, because there is that motion, that movement of individual parts of their body. All that is a force that is absorbed, right? That momentum gets absorbed in different parts of the body. That momentum gets absorbed by the grass. It gets transferred to outside forces. So these collisions don't work exactly like we describe them in these equations, because these equations don't take into account outside forces. But in order to be able to take into account outside forces, which is the ultimate goal of physics, is to describe the whole big picture, we have to understand where we start, and then we layer on all those pieces. So conservation of momentum is telling us the basic principle that we can layer all of this on. So we see this with train cars, all right? If this blue train car is moving at 4 meters per second, the green one is moving at 2 meters per second, we know just by thinking about it that this one is going to catch up. This is moving twice as fast, is ultimately going to catch up. If this train car has a mass of 2 kilograms, which, by the way, this would be like a toy train car, right? That's a little bit less than 5 pounds. 2 kilograms times 4 meters per second. And so this train car also has a mass of 2 kilograms. The total momentum is 12 kilogram meters per second, or 12 Newton seconds. And then we have here afterwards, right? These collide. And afterwards we find that this green one is moving at 4 meters per second. This blue one is still moving at 2 meters per second. So some of that momentum has been transferred from the blue car to the green car. However, afterwards, the total momentum is still 12 kilogram meters per second. Again, in reality, a lot of this momentum is lost, is transferred, I should say. I shouldn't say lost. Is transferred to friction, to outside forces, all right? If this were like a gas tanker car, well, maybe it explodes, and then there's all sorts of potential energy that gets transferred to kinetic energy, and so on and so forth. Obviously, it can get really complex really quickly. We're just focused on this. In our ideal scenario, we start off with 12 Newton seconds of momentum. We finish with 12 Newton seconds of momentum. So now we can talk about this difference between what are called elastic and inelastic collisions, meaning that that last little slider that you had about how elastic the collision was going to be on the lab. Now, we only considered 100% elastic collisions. And this Newton's cradle on the left-hand side here is an example of an elastic collision. All right, so it's bouncing. So the momentum of the ball on the left is getting transferred through all of these balls in the middle to the ball on the right, and vice versa. All right, but what if these things, when they collide, that they don't move, or that they move as one? Okay, so if a watermelon hits concrete from a high from a high location, that momentum will be transferred of the watermelon. It will be transferred to the system of the watermelon and the ground. And because the Earth is so big, we don't actually notice any change in momentum of the Earth, but it does change ever so imperceptibly. Right? That would be an inelastic collision. They collide and they move as a unit. And so if we imagine 2 objects, 2 balls, one mass moving towards the other, when they collide, maybe one is sticky, and they don't bounce off of each other, and they start to move as one unit, well, they will move in whatever direction the momentum is greater. So let's go back to our 2 football players. We've got football player number 1, who had a bigger mass and a bigger velocity and a bigger momentum, all right, like this guy right here. And football player 2, smaller mass and smaller velocity, they hit each other. And let's say player 2 is holding on to player 1 with everything they've got, so they move as one unit. They don't bounce off of each other, they're moving as one unit. Well, they're going to move in whatever direction player 1 was moving in to begin with, because player 1 has more momentum, and so they'll move in this direction with 200 Newton seconds as one unit. All right, that's an inelastic collision. The 2 objects stick together after the collision so that their final velocities end up being the same. Obviously, that velocity is going to be much smaller because the total mass of that final object is much bigger. All right? So let's consider this with a simpler example rather than going all the way to the football players. Let's consider this with some fish. So we have a 6 kilogram fish. That's a big fish. It's a 14-pound fish. So got a 6 kilogram fish swimming at 1 meter per second. All right, just kind of lollygagging along. And it swallows a 2 kilogram fish that is at rest. A 2 kilogram fish is not moving. Let's hope it was still alive before it got eaten. Find the velocity of the fish immediately after lunch. Note that the momentum initially is equal to the momentum finally. So the initial momentum is equal to the final momentum. Okay, so how are we going to set this up? We know momentum is equal to mass times velocity. So what is the momentum of the first fish? Awesome. So the momentum of the first fish, 6 kilograms times 1 meter per second, gives us, I'm just going to use Newton seconds because it's shorter. It gives us 6 Newton seconds. What is the mass of the second fish? What's the velocity of the second fish? It's not moving. So what's the momentum of the second fish? And then what if the momentum of that, what if the mass of that second fish were 200 kilograms instead of 2 kilograms? What would be the momentum of that fish? Hint, it's the same answer. Right, so anything that's not moving has 0 velocity and therefore no momentum. Okay, so the total momentum, the initial momentum is going to be 6 Newton seconds, which means what is going to be the final momentum? Final momentum is 6 Newton seconds. All right, so here's where we get math. That final momentum so I'm going to use P sub F, or just P F here. I'll put it in parentheses to make it obvious that it's a, make it more clear that it's a subscript. So the final momentum is going to be equal to the total mass times the total velocity. All right, and I hope that notation makes sense that I'm writing in the chat. I would do it on the slide, but I don't have a lot of room on this slide. Wasn't thinking ahead. So we know that that final momentum is 6 Newton seconds. What is the total mass of this big fish that has eaten the smaller fish? What is the total mass? So Isabella, you're suggesting that the total mass is 8 kilograms, and I agree with you. I disagree with what you've set up as step 2, though, because we know that the final momentum has to be 6 Newton seconds. The final mass is 6 kilograms plus 2 kilograms, because the first fish is 6 kilograms and the second fish is 2 kilograms. And it's up to us to figure out what that total velocity is. Oops, I messed up. I shouldn't say TV, that should say VT. So let me rewrite it appropriately. So the total velocity of the system, of this little fish that has been eaten by the bigger fish, we're going to have to calculate by dividing both sides by what? Awesome. So if we divide both sides by 8 kilograms, we get 6 Newton seconds divided by 8 kilograms, which we know is going to be 3/4, or in decimal form, 0.75 seconds. Now let's think about this for a minute. This fish, the 6-kilogram fish, was swimming at 1 meter per second. I'm sorry, not seconds. Thank you, thank you. That's a velocity, not a time. That should be meters per second. So this fish was swimming at 1 meter per second. And now that it has eaten the smaller fish, it is now traveling at 0.75 meters per second. It is slowed down. This should make sense in your head. The reason I'm pointing that out is that when you're doing these calculations, estimate in your head. Should it be bigger? Should it be smaller? Should it be the same? Should it be much bigger? Should it be much smaller? Get an idea in your head of what we're describing in reality, because if your answer doesn't match that, then that means you probably did something in the math that's incorrect. Always do that estimating piece. And I know your math teachers have told you this time and again about estimating and how important estimation is in order to be able to see if your answer makes mathematical sense. So always do that piece. And when we think about it, we go, hey, this 6-kilogram fish, this really big fish, swallows this smaller fish. Well, of course it's going to be moving slower. Now it weighs more. So it's going to have less velocity with the same momentum. Okay, so now we see situation 2, all right? Second bullet point here. That same 6-kilogram fish swimming at 1 meter per second swallows this same 2-kilogram fish, but this time that fish has a death wish apparently and is swimming precisely towards this bigger fish at 2 meters per second. So that tells us something about our calculation. We know that the first fish has 6 Newton seconds of momentum. So remember the football player example. What is going to be the momentum of this second fish? And I'll use 2 as a subscript here. The momentum of fish 2 equals the mass of fish 2 times the velocity of fish 2. Ah, a wild negative sign appears. Wonderful. So the momentum of fish 2 equals 2 kilograms times negative 2 meters per second. That is super important. And the reason it's negative is because it's moving in the opposite direction as the first one. Again, you could attach that negative sign to the first fish. It would just mean that the ending answer would also be negative. So whatever direction you dedicated as negative, you would just have to be explicit about that in your explanation. So we end up with a momentum of -4 Newton seconds for that second fish, which means what is the total momentum of the system? Total momentum of the system, we add the two momentums together, or momenta. So we add momentum 1 to momentum 2 to get the total momentum of the system, which is 6 Newton seconds plus a -4 Newton seconds gets us 2 Newton seconds. Beautiful. So that final momentum we know is going to be 2 Newton seconds. So if we again apply it to our finals, our final momentum is 2 Newton seconds. Our final mass is still going to be that 8 kilograms. And I said, well, I shouldn't talk and type at the same time. I put plus in there, and I meant to write times. So 2 Newton seconds equals 8 kilograms times some final velocity. Again, we're going to divide each side by 8 kilograms, and that will get us our final velocity. 2 divided by 8 is 0.25 meters per second. And so the two fish, well, the one fish inside the other, are now moving at 0.25 meters per second. They've started moving very slowly. Let's consider this last one, this last example here, where the second fish still has a mass of 2 kilograms, and it's moving at 3 meters per second in the opposite direction. What does that make momentum of fish 2? Excellent. And so when we add those two momenta together to get the total momentum, we're adding 6 Newton seconds plus a -6 Newton seconds, which gets us a total momentum of yeah, 0 Newton seconds. All right. So we know in this case that the final momentum of 0 Newton seconds needs to be equal to 8 kilograms times what? What does that velocity have to be? The final momentum, if the total momentum at the end has to be 0 Newton seconds. Yep, the fish isn't moving, folks. So, and here's how you should visualize it. That big fish is moving slow. The small fish is moving fast. When they collide and they don't bounce off of each other, they stay still. All right, this is why offensive linemen in football have such huge mass. This is why they weigh upwards of 300 pounds. They are trying to establish momentum without establishing speed in order to create an inelastic collision so that they prevent the defense from getting to their quarterback or getting to the running back. So they are trying to create that inelastic collision by having a lot of momentum and equaling the momentum or being greater than the momentum of the player coming at them. All right, so looks like we have a little over 20 minutes to finish up the collisions lab. Again, do your best with that. If you're not finishing it up, but you're obviously working your hardest, then I've got no problem with that. Do as much as you can on it. If you finish it with it, then make sure that you do momentum and impulse today. Let me know how far you get with that, because understanding how impulse works, especially with this lab, is something that will serve you well for further scientific pursuits, especially as it comes to the STEM track. Okay, so again, you should be either finishing with the collisions lab or doing as much as you can with the momentum and impulse lab. Any questions?